Alright, I'm going to read a really interesting article from the WindowsNT magazine, September 1997. This is written by Mark Russinovich, so you know it's going to be good. He begins writing, WindowsNT is a preemptive multi-threading operating system. That is, NT lets several programs run simultaneously and switches among them, often enough to create the illusion that each program is the only program running on the machine. Well, that's the idea anyway. How to smoothly share one CPU or multiple CPUs among many threads of control is a complicated problem. Solving this problem dynamically many times per second is the job of the NT scheduler. The NT scheduler must honor the relative priorities that the application's programmers designate for each thread and attempt to provide responsiveness to user interactive threads. In this first part of a two-part series about the algorithms NT's scheduler employs, I'll introduce basic information about the NT scheduler. You'll find out about the priority levels that NT assigns to threads, how Win32 programs specify priorities for their threads, the situations that invoke the scheduler, and the algorithms NT uses on uniprocessors in those situations. So this first section is titled Threads and Priorities. The basic scheduling unit in NT is a thread. A thread is a point of control within a process. Processes consist of a virtual address space that includes executable instructions, a set of resources such as file handles, and one or more threads that execute within its address space. Typically, applications consist of only one process, so program and process are often used synonymously. Most programs are today single-threaded, which means they run as one process with one thread. However, multi-threaded programs are becoming more commonplace. An example of a multi-threaded program is a program that lets a user sort a list with an option to cancel. One thread in the program's process might perform the CPU-intensive sorting task, while another thread in the process displays a how to cancel message to the user and waits for a response. The scheduler does not differentiate between threads of different processes. Instead, the scheduler examines the priorities of all the threads ready to run at a given instant to pick which thread to execute. NT assigns each thread a priority number from 1 to 31, where higher numbers signal higher priorities. NT reserves priorities 16 through 31, aka real-time priorities, for use by time-critical operations. Only a user with administrator privileges can direct the system to execute threads in this range. NT uses priorities 1 through 15, aka dynamic priorities, for the program threads of typical applications such as Notepad, Word, Lotus Notes. And that last example kind of dates this article. Remember, we're in 1997. He goes on to say that the NT kernel provides functions that let you set a thread to any of the 31 priority levels, but the Win32 API is more indirect. In Win32, specifying a thread's priority is a two-step process. You must first set the priority class of the process, then you can apply a relative priority to individual threads. A process priority class is a priority level around which NT lets the process threads execute. The Win32 API defines 4 priority classes: real-time, high, normal, and idle. These names correspond to priority levels 24, 13, 8, and 4. What a weird way for Dictate to list out those numbers that way. Well, he goes on to write, setting a process priority class causes all the threads of that process to begin executing at priorities within plus or minus 2 of the class priority. This scheme is shown in Figure 1. New processes inherit the priority class of their parent. Process threads start at the priority level associated with their process priority class. So here's Figure 1. Priorities and process priority classes are 0 through 31 column. Let's go ahead and take a sneak peek at Figure 2 and Figure 3. This one is relative priorities within the normal priority class, so lowest to highest. Figure 3, find ready thread, picking the highest priority thread. So this is the dispatcher ready list. Okay, we'll get there in the reading. The relative priorities that can change a thread's priority from its process class priority are highest, above normal, normal, below normal, and lowest. The Win32 API includes 2 special case priority modifiers, time critical and idle. Time critical moves the dynamic thread's priority to the top of the dynamic range, which is 15, and idle moves it to the bottom, which is 1. This next section is titled, Whose Turn Is It? Threads must take turns running on the CPU so that one thread doesn't prevent other threads from performing work. One of the scheduler's jobs is to assign units of CPU time, called quantums, to threads. Alright, and they spelled quantums correctly up here. A quantum is typically very short in duration, but threads receive quantums so frequently that the system appears to run smoothly even when many threads are performing work. One difference between NT Server and NT Workstation is the length of a user's thread's quantum. On most x86 systems running NT Server, a quantum is 120 milliseconds. On x86 systems running NT Workstation, a quantum can be 20 milliseconds, or 40, or 60, depending on your system setting and whether the thread is a background or foreground application thread. He promises to write more on this topic later. So the scheduler must make a CPU scheduling decision every time one of these three situations occur. Either, number 1, a thread's quantum on the CPU expires. Number 2, a thread waits for an event to occur. Or number 3, a thread becomes ready to execute. When a thread's quantum expires, the scheduler executes the find ready thread algorithm to decide whether another thread needs to take over the CPU. If a higher priority thread is ready to execute, it replaces or preempts the thread that was running. In many cases, threads perform processing and then wait for an event to occur. For example, a client-server application might have a server thread that performs processing when it receives client requests and then waits for more requests. A waiting or blocked thread gives up its quantum early, and the scheduler must execute the find ready thread algorithm to find a new thread to run. When a new thread or a blocked thread becomes ready to execute, for example, when the client-server application server thread receives another request, the scheduler executes the ready thread algorithm. This algorithm determines whether the ready thread will take over the CPU immediately or be placed in an eligible to execute list. Find ready thread and ready thread are the key algorithms the NT scheduler uses to determine how threads take turns on the CPU. The uniprocessor versions of find ready thread and ready thread are straightforward algorithms. Okay, so I'm going to skip the next few sections where he really goes into detail about these two algorithms. I'm also skipping the section where he talks about boosting and decay. Well, maybe I'll say one thing about the boosting section. So he writes another type of boost NT Workstation applies as a foreground application boost, which you can control from the Performance tab of the System Applet in Control Panel, and you can see screen 1 for that. So because I think that's kind of cool, I'll go ahead and show you here. And I've really tried to zoom in. You can see this is a pretty typical Windows box we're looking at here. Okay, so that's pretty cool that you can control this. He said this type of boost affects a quantum length rather than priority. For the default maximum setting, NT extends the quantums of foreground application threads to 60 milliseconds. If you position the slider in the middle, NT sets the quantums to 40. If you position the slider on none, the quantums are 20 milliseconds, the same as the quantums of background application threads. The last real section of this article is titled Starvation Prevention. Left alone, the find ready thread and ready thread might prevent low priority threads from getting a chance to execute. So for example, a priority 4 thread running on a system with continuously running priority 8 threads would be starved for CPU time. However, NT provides a mechanism that gives low priority threads a shot at the CPU. The NT Balance Set Manager is a system thread that wakes up every second or so to perform memory tuning. As a secondary responsibility, Balance Set Manager executes the Scan Ready Queues algorithm, which implements NT's anti-CPU starvation policy. So the Scan Ready Queues scans the dispatcher ready list. Working down the list from priority 31, it looks for threads that haven't executed in more than 3 seconds. When it finds one, Scan Ready Queues give the thread a special anti-starvation boost, doubles its quantum, and calls ready thread with the thread as a parameter. The anti-starvation boost differs from other boosts instead of applying a relative priority increment. The anti-starvation boost slams the thread's priority to the top of the dynamic range. On pre-Service Pack 2 SP2 systems, the anti-starvation boost was to priority 14. Post-SP2 systems boost to priority 15. So we see a little tweak there when you update Windows. When a thread that receives an anti-starvation boost finishes its extended quantum, or the thread blocks, its priority returns to pre-starvation boost level and its quantum returns to its usual length. So the last paragraph is just him promising to tell us more next month. There's a little about the author at the very bottom. Mark Russinovich holds a PhD in computer engineering from Carnegie Mellon. He's an NT internals consultant with Open Systems Resources in New Hampshire. And I wonder if this website still works, ntinternals.com. Okay, that's it for this video. Thanks for watching.